Hello. So, good evening, everyone. I am Sanju Kumawat, and welcome to the 8th live section of the NPTEL course Design of Reinforced Concrete Structure. So, today we will be studying about the curtailment requirements in a slab. So, in the previous classes, we have studied about the curtailment requirements of beams, and now today we will be studying the same about the slabs. So, let's begin with this class. Okay, so the design of the one-way slab, whether the slab it is continuous or it is simple isolated slabs, the designing of both we have seen in one of the live lectures. I think it was the live lecture 6. So in that lectures we have seen the designing of one-way slab. So what was one-way slab? One-way slab was nothing but a slab whose either the Ly by Lx ratio is greater than 2, or if it is supported on only two of its opposite sides. So if a slab, if it is supported only on two of the sides, then we say that it is a one way slab irrespective of what Ly by Lx ratio is. So in this way what we do, we classify the one way slab. Now let's look at the curtailment requirement in a slab. So as we can see, you all can see that the curtailment requirement for a continuous one-way slab has been displayed over here. So what is curtailment requirement? You all know. In order to economize the device, what we do, we cut the flexural bars from the position where it is no longer required to resist the movements, and the bars which are then present at that point after the curtailment, they are responsible for taking all of the movements into the section. So let's now see what are the curtailment requirement in one way slab for a continuous one way slab. So these are the 4 points which you all have to remember. So curtailment, it normally occurs for the tensile reinforcements. So okay, so that's quite obvious, like we provide the tensile reinforcement for the resistance of flexure forces. So that tensile reinforcement, either it can be provided into the positive side or it can be provided into the negative side. So as I also said you this in the previous class, for example, this is our continuous slab or a beam, then what will be the bending moment diagram? The bending moment diagram will be something like this. Okay, so if you look at the continuous section, this continuous section, if you look, so between this continuous section you have both negative as well as the positive bending moment. So for this positive as well as negative bending moment, what you will have, you will have reinforcement on both top of the slab as well as at the bottom of the slab. So here you can see I have provided the reinforcement at the bottom of the slab. So this reinforcement is responsible for resisting the positive bending moment. And other than this, we have reinforcement at the top of this slab also. So let me change my color of the pen because there are red marks already in the figure. So here you can see there are bars at the top as well as there are bars at the bottom. So we, because we have two types of movement, positive as well as negative movement in this slab. So now we will have to study the curtailment requirement for both of this tensile steel, that is for the positive steel also and for the negative steel also. So what's the first point says? The first point says that tensile reinforcement provided at midspan shall extend in the lower part of the slab to within point. So don't get just scared of these statements. Firstly, all of you answer me this question. Suppose we have a slab. So if we have a slab and the bending it occurs in this way, okay, so if the bending it occurs in this way, then where will I provide the tensile bars? Whether I will provide it at the top or at the bottom?
At the bottom.
So at the bottom, I will provide the tensile reinforcement if by sagging it occurs. So now what happens? Okay, so I have some answers in the chat box also. I will have to keep a track on them. Okay, fine. So what the first point says? The first point says that the tensile reinforcement. So don't get confused with this statement. Tensile reinforcement, tension reinforcement, it can present at the bottom as well as at the top. So what does it says? Tension reinforcement provided at the midspan shall extend in the lower part of the slab. Okay, so the tensile reinforcement means this AS1. It should extend in the lower part of the slab to within 0.25 L of continuous edge or 0.15 L of its discontinuous edge. Okay. So which are all the continuous and the discontinuous edge? So this is the continuous edge and this is the discontinuous edge. So my bottom reinforcement, it should extend up to a point which is 0.15 L from the discontinuous edge, and it should extend up to a point 0.25 L from the continuous edge. So that is not very difficult, I hope. Now, what's the next point says? At least 50% of the tensile reinforcement provided at the midspan shall extend to the support. Okay. So here you can see I have curtailed the bar. Here you can see I have curtailed the bar at this point, but at this point I have curtailed the bar, but still you can see there is some continuation of bars. This is the curtailed bar, the bent up part, you if you can see it here. So this is the curtailed bar, and only 50% are curtailed. Every alternate 50% bars are curtailed and alternate 50% bars are extended into the support. So that's what the second point it means to say. Third point, it says over the continuous support, the tensile reinforcement shall extend in the upper part of the slab a distance of 0.15 from the support, and at least 50% shall extend up to a distance of 0.3 L. So this is the continuous edge. So at the continuous edge, now about which tensile reinforcement it is talking about, over going the tensile reinforcement shall extend in the upper part. In the upper part means I am talking about the bars which are resisting negative moment. So here you can see the bars, it should extend up to a distance of 0.15 L from the edge, and about 50% it should extend about zero point 0.3 times of L. And the fourth point, it says tension reinforcement at the discontinuous support shall extend at a distance. Okay. So here you can see what we are trying to do. We are curtailing the bars for continuous and discontinuous edge. Okay, so we have two cases, and now the other two cases we have at the continuous edge. I have the bars at the top and at the bars at the bottom, and the discontinuous edge I have bars at the top and the bars at the bottom. So for the discontinuous edge, the bars which are located at the top, they should extend up to a distance of 0.1 N, as you can see it here. So this was all about the continuous one-way slab detailing, and the problem I have already taken it in the previous classes. You can all draw the reinforcement detailing for that problem. It is not that difficult. Now let's move on to two-way slabs. So for two-way slabs, I can have these two types of two-way slabs. In one-way slab, can any one of you tell me what were the types in one-way slab? Please tell me fast. What were the two types in one-way slab? How to identify a one-way slab? I just answered it. Maybe you both have not
Ly by Lx greater than 1, greater than 2.
greater than two. And what was the other condition?
Uh, Other condition? Don't know, sir.
Okay, so I told you in the last class, in the previous lecture 6, either Ly by Lx, it should be greater than 2. This is the first condition for a slab to be classified as one-way slab. And the other condition is irrespective of this ratio, if my slab it is supported only on two sides, only if it is supported on only two sides, then whatever may be this ratio, I will classify it as one way slab. Okay. And if it is supported on four sides, then I will have to see this ratio. But if it is supported on only two consecutive sides, then I will simply classify it as one way slab. Okay, so just remember these two cases for one way slab. Now I will talk about two way slab. So this is the two way slab. Two way slab can be classified into these two types, that is the corners can it can be either unrestrained or it can be restrained, and both of them can have simply supported condition. And here I can, based upon the support condition, I can have nine different cases. So I will make all of these nine cases very simple for you. Just remember the number types of one-way slabs, either Ly by Lx greater than 2, or it should be supported on only two sides. For two-way slabs, I can have these two conditions: corners unrestrained and corners restrained. Corners unrestrained means what? My corners can lift up like this. Means they are not resisted by any torsional reinforcements. Corners restrained means I have provided the torsional reinforcement because of which my corners are remained at its position. And based upon the different types of support condition, whether my longer edge is continuous or my shorter edge is continuous or discontinuous, based upon all of these cases I have, based upon all of these conditions I have eight other conditions. And what all are these eight conditions we will be seeing just in a minute. So these are all the nine conditions. These nine conditions I will be making more simpler for you in the next slide. Okay, so let's talk about this 9 condition. Okay, so this is a roof slab, and all the different types of slabs which I previously classified are present in this single figure. So the one which is named as one, what type of slab this is? This is
Interior slab.
this is an interior slab, and broadly speaking, what we can see, this slab has its shorter as well as the longer edge continuous. Sorry for the bad writing; it is very difficult to write on electronic screen. And now let's talk about the slabs which are named as two. What this slab have? This slab has three continuous edges. It has three continuous edges, but one short edge is discontinuous. Similarly, third is this. So it has one long edge discontinuous. What is the fourth condition? Fourth slab, not condition. Fourth slab is one short and one long are discontinuous. What is the fifth type of slab I have? This is the slab with one long edge as continuous. Only one long edge. All of the three are discontinuous. Sorry. It has two long continuous, or I can say two short discontinuous. Okay, sixth. What is the sixth one? Sixth one is two long discontinuous. So all of the types of slabs we have covered in this figure. Seventh one is only one long is continuous. What is eighth one? Eighth one is only one short is continuous. And what is ninth one? Who will answer? What is ninth one? What type of?
Four edges
All
discontinuous.
of the edges are discontinuous. Okay, so let me display the answer. So as you can see it here, all of the 9 cases have been covered up in this figure. Okay, so these were all the types of slab. Now let's understand what is the purpose of classifying these two-way slabs into these 9 different conditions. Okay, so a two-way slab, it appears something like this. Two-way slab, it will bend in both direction, in the x direction as well as in the y direction. So here I will design the two-way slab based upon the design of this strip which I have hatched. So this strip, first of all, we take this strip of dimension 1000 by 1000 and we design it. And there will be moment coefficient. Those moment coefficient will be alpha x, alpha y, depending upon the edge is continuous or discontinuous. My alpha x and alpha y, we will have alpha x positive, alpha x and alpha y positive, and alpha x and alpha y negative. Alpha x and alpha y will be negative at the edges, because at the edges what we have negative moment. That's why this classification is important, because the edges which are free, can anyone tell me the edges which are free, what will be the moment at the edge? Suppose this is my continuous span, and now if I draw the diagram, it will appear, bending moment diagram, it will appear something like this. So what is the negative moment at this free edge?
Zero.
It is zero. So moments at this free edges would be zero. At any free edge it will be, at any discontinuous edge it will be zero. So now let's see what I am trying to, why we have classified it in this 9 type. You will understand it in the next slide. So basically the design of slab, it is based upon the distribution of my slabs into number of strips. So we basically divide the straps in the longitudinal as well as in the, both the sides are longitudinal only. So I am dividing it in the longitudinal as well as in the transverse direction. You can see it. I am dividing it into small strips. This is the edge strip, this is the middle strip, and the middle strip, it is 3/4 of the entire span, both for the longitudinal as well as the transverse direction. And now you will see how the moments work. I have divided this slab into the strips because at the edge strip I will have negative moment, So H can have negative moment or it cannot have negative moment based upon its continuity. And here you can see alpha x is negative and alpha phi is negative for the edge. These are edges. And alpha x and alpha y are positive for the midspan, because at the midspan what I have, the moment is positive. Okay, now let's see how we do the design of two-way slab. So two-way slab design, it is mainly based upon these two coefficient alpha x and alpha y. Alpha x and alpha y based upon the different uh, edge conditions, alpha x and alpha y changes. And here we have total of 9 cases. So we will one by one we will see how to read this table. So table 26, it what it gives, table 26 of IS 456, it gives us bending moment coefficient for rectangular panels supported on four sides with provision for torsion at corners. So what does this means with provisions at torsion at corners? Whether it is restrained or not restrained? So
Restrained.
it is restrained, fine. So now first case is, now I want you to remember 2 to 3 points about this table which will be very helpful. First of all, depending upon the continuity condition, I can get the moment coefficient alpha x and alpha y from this table. So this is the short span coefficient. Short span coefficient is alpha x. So if my bending, if it is along the shorter span like this, so this will be my alpha x. So along shorter span, along longer span, it will be alpha y. So I will have to find the alpha x and alpha y. So shorter span coefficient, first point is shorter span coefficient, it depends upon the ratio Ly by Lx, while the long span coefficient, it does not depends upon Ly by Lx. It is constant depending upon the type of continuity we have in the slab. This is the first point. Second point, what you need to remember, at any so here you can see I have, for any type of slab I have two coefficients here, the negative moment at continuous edge and the positive moment at midspan. At the midspan my moment will be always positive, while at the edges it will be negative. And that negative moment will be only for continuous edge. Everywhere if you see, the continuous word is mentioned. Sorry, not this, continuous. So the negative moment, it will be present only if my slab is continuous, and at any point where the slab is discontinuous my moment will be taken as 0. So this is the second point which you need to remember. First point is Ly by Lx, it, the alpha x, it varies with Ly by Lx. Second point is at any discontinuous edge my negative moment is 0. So these are the 2 points you have to remember. And the third one is, there is a small mistake in IS 456. Instead of discontinuous, here the case should be, instead of continuous the case should be discontinuous. And now based upon these 2 points which I have told you to remember, can you answer me why these values are not specified for the fifth case? Let's first talk about the fifth case. Why the alpha y coefficient for the two short edge discontinuous is not specified? Two short edge is discontinuous. For example, if I take this diagram, so my this is continuous, so there is a slab like this, long edges are continuous, but my short edges are discontinuous. So why this is 0 alpha y? Did you understand what I am trying to say? Why this is not defined? For fifth case, why alpha y is not defined? Okay, so let me answer this. Just a minute before I told you, at any discontinuous edge my moment, negative moment coefficient will be 0. So what the fifth case says, two short edges are discontinuous, means this is the first short edge and this is the second short edge. So these two short edges are discontinuous, and the bending along these two short edges is bending like this. So this is bending for what? This is bending alpha y now, but this is discontinuous. So for discontinuous edges alpha y is 0. That's why this is not defined. Did you get me? Why it is not defined? This can be a competitive exam question. Now the sixth, yes, any question? Sure.
No, sir.
Okay, so sixth one, in the similar fashion, you can see why these are not defined. Two long edges are continuous. Two short edges are so two long edges are discontinuous. So now this is continuous and this is continuous, but these two are discontinuous. That means alpha x will be not defined. Okay, that is fine. Are you getting me? For any discontinuous moment, my negative moments are absent. Now three edges are discontinuous. Three edges are discontinuous. One short edge is continuous. This all are discontinuous. What does that means? My alpha y will be not defined. And for the fourth case, there would be no negative moments because all of them are discontinuous. So alpha x minus and alpha y minus both will be absent. So this was the logic behind this table. I hope you all got this. Now let's move on further. Okay, now the most important part, the curtailment of a reinforcement in two-way slab. So this is a bit difficult to understand, so pay attention. So we have already seen the curtailment of bars in the continuous one-way slab. Now we will be seeing it for the two-way slab. So what does the first point says? The tensile steel calculated for the positive design moment MUX and MUY should be provided at the bottom of the midspan and uniformly distributed across the middle strip in the short and the long direction respectively. So what it is trying to say, let's understand it with the help of this figure. So it is trying to say me that the tensile reinforcement which we are providing it at the mid strip, it should be uniformly distributed. Okay, so it is talking about this reinforcement, the black one. So black one is the bottom reinforcement. So the bottom reinforcement we are providing it at the mid span because at the mid span we have positive movement and positive movement will always have reinforcement at the bottom. So we are talking about this reinforcement. So this reinforcement it should be provided both for MUX and MUY and they should be uniformly distributed across the middle strip in the long and the short direction. Okay, so I hope that was clear. Now let's move on to the second point. Tension reinforcement provided at the midspan. Again, we are talking about the reinforcement at the midspan. That is for the reinforcement provided at the bottom in the middle strip. So I already told you we are dividing the slab into middle strip and the edge strip. In the edge strip, we provide the negative reinforcement, while in the middle strip, we provide the positive reinforcement. Here we provide positive reinforcement. Here we provide negative reinforcement. So now we are still talking about the positive reinforcement only because we are talking in the middle strip. Shall extend in the lower part of the slab to within 0.25 of the continuous edge or 0.15 L of the discontinuous edge. So this is similar to the point which we have covered in the one-way slab. And at least 50% of this reinforcement shall extend to the support. Same point we have covered in the continuous slab. So what it is trying to say, this reinforcement it should extend up to 0.15 L from the edge of the support and for the discontinuous edge, and for the continuous edge it should extend by 0.25 L and only 50% of the bar should extend. 50% of the bar should be curtailed and 50% should be curtailed. So every alternate bar we will curtail and every alternate bar we will extend it to the support. So this was all about the reinforcement, positive reinforcement which we provide into the middle strip. Now let's talk about the third point. The tension steel calculated for the negative design moment. Now we are talking about the bars which we will provide in the edge part. Okay, because in the edge we provide negative reinforcement. That is the reason we like distributed my slab into different numbers of strip. So now the negative moment at the continuous support should be provided at the top and uniformly distributed across the edge strip in the short and the long span direction respectively. So what else it is trying to see? Now we have already finished the provision of bottom reinforcement. Now we are talking about the top reinforcement. So what it is saying, the top reinforcement, what it is saying, the top reinforcement it should be provided at the top and uniformly distributed across the edge strip. So these are the edge strips. So we have to uniformly distribute the bars into the edge strip. Now let's talk about the curtailment of the bars. Over the continuous edge of middle strip, the tensile reinforcement shall extend in the upper part of the slab at a distance of 0.15. So this is also similar to one-way slab, and at least 50% should extend up to a distance of 0.3 L. So here you can see these are the top reinforcements, the one which are highlighted in dot. So 50 percentage of them should extend only up to a distance of 0.5 L. So where it is, so this is for the continuous edge. So for continuous edge, 50 percentage of it should have only 0.15 L, and other 50 percentage should have 0.35 L, that is double of 0.15 at the continuous edge. Here also you can see in both directions. So the first one being this 0.15 L, and the other is double of 0.15 L. So this was about the reinforcement in the positive part, sorry, in the upper part. And when we talk about the reinforcement in the negative part, this was the reinforcement in the negative part. That is 50% should extend into the support and 50% should be curtailed in both the directions. Okay, so these were all the 4 points. Now let's talk about the fifth point. At discontinuous edge, negative moments may arise due to partial fixity. Hence, a safeguard. Okay, so at discontinuous edge, what we are assuming? We are assuming that the moment will be zero. But what now this clause says? It says due to partial fixity, there can be a case where moment can arise. Hence, to safeguard against this moment, 50% of the bottom steel at the midspan should be provided at this edge, and such steel should extend over a distance of 0.15 lx or 0.0 ly from the face of the support. So now at the discontinuous edge, I am not supposed to provide any negative bar because we are assuming zero negative movement. But at discontinuous edge, there can be accidental moments, and because of which I have to provide some bars. So these are the bars which are provided at the discontinuous edge, and it should extend 0.15 L from the edge of the support. As you can see, at both the discontinuous edge, I have these bars. Okay. Now, distribution reinforcement in the edge strip parallel to the edge shall be provided to satisfy the minimum area of tensile reinforcement. Okay, so based upon the requirement of tensile reinforcement, what I am saying now, see, we will always provide bars like this, but now the code asks me to provide bars parallel to the edge into the edge strip like this. Means these bars will be this one. So these are distribution bars. They are also to be provided in order to fulfill the area of reinforcement required, and this reinforcement will be parallel to the edge. For this edge it will be like this, for this edge it will be like this. So there are too many bars. If you can see it here, it is very congested. So this was all about the curtailment of bars in a two-way slab. If you have any doubt, you can ask me right now only.
Sir, my previous question was that when there is curtailment, then 50% is at the top and 50% at the bottom of the slab. So the means the tau c value that we calculate for the shear for check for the shear, in that AST value is reduced. Is that correct or not?
Yeah, AST value is reduced, and we have seen this in the previous class.
Yes, sir. It was in case of beams, but here it was slab. So, sir, when we calculate the percentage, then it comes less than 0.15%,
Yeah,
where we
the,
calculate tau c value from the table.
yeah, and
From
that
the
is the
ta-
reason the last clause it says distribution reinforcement it should be provided to satisfy the minimum area of tensile reinforcement together along with the recommendation of torsion bar.
what does this mean? Please explain.
It says in order to satisfy the minimum amount of, like in the IS code we have what amount should be the minimum area of steel which we should provide. So in order to satisfy that minimum area of tensile reinforcement, we would be providing distribution reinforcement which will be present parallel to this edge.
When there is when it is parallel to the edge, even if the one transfers to these bars,
Yes.
then it they will be curtailed, na?
Yeah, but this bars will be provided in both the direction here also.
Uh,
In the edge
yes,
parallel to both the edges.
yes, sir. But in between, sir, means these are at the edges.
These are at the
Uh,
edges.
uh,
And
but the
shear is,
bars in transverse direction, they are just curtailed. They are at the top and at the bottom.
yes.
Then in that case, it is getting reduced to less than 1.5%, 0.15%.
Okay.
So my question was tau c value for that M20 grade, for M20 grade, then we'll go for that value only.
No, we won't go by that value. That's what this distribution reinforcement, because shear reinforcement it is predominant at the edges, if you know. And to satisfy those shear requirements, or to satisfy the minimum area of tensile reinforcement, what we do, we provide these bars.
Okay, sir. But these are parallel to the edges, but those are in transverse direction. So isn't that affecting, means some kind of effect is there?
The bars won't have any effect. It will be present here, parallel to this edge and parallel to this edge, everywhere.
Okay, sir.
Okay. So just like one more time, I know it is difficult to understand, and for me also it was difficult. I am not. I will agree this also, but I will just suggest you to go through these clauses one more time, because these are some of the important points that you should try to understand. And there is a lot of reinforcement curtailment in this two-way slabs, and it may create a lot of confusion. So please kindly go through this slide once more time. Now let's proceed further for today's class. So now let's talk about the torsional reinforcement. So torsional reinforcement, the first point is torsion reinforcement. It is provided at the top and at the bottom in a mesh grid, in a mesh or grid pattern, each with layers of bars placed parallel to the sides of slab and extending from the edge to a minimum distance of one fifth of the shorter span. Okay, so the shorter span it is Lx, and the torsional reinforcement it is provided in the form of a mesh. That is, it is provided like this in a form of a mesh. It will have a length of LX, each with layer of bars parallel to the sides of the slab and extending from the edge to a minimum. Okay, I hope you understand this. The second point is the area of reinforcement in each of these four layers. So there will be four layer. How I at each corner of the slab I will have, this is two layers. At the top I will have two layers, and at the bottom I will have two layers. So in this way I have four layers, and the total area of this four layer it should be having a maximum area of 0.75 times the ASTX, that is the area of steel which is provided in x direction. The third point it says torsion reinforcement equal to half that described in 2, that is in the point number 2, that is half of 0.75, that is 0.375 of ASTX. It should be provided at a corner where one edge of the slab is continuous and the other edge is discontinuous. So like this, one edge is discontinuous as one edge is continuous, then I will provide half of 0.75. Okay, while at this edge if both edges are discontinuous I will provide 0.75 ASTX. And if it is, the last point says torsional reinforcement need not be provided when both the edges meeting at the corner are continuous. So if this is the case, if I have to provide torsional reinforcement at this, both of the edges are continuous, so there will be zero torsional reinforcement. So this was all about this torsional reinforcement. So if both of the edges are discontinuous, 0.75, one edge is discontinuous, one edge is continuous, 0.75 by 2, all of the edges are continuous, zero torsional reinforcement. Now let's, okay, so I have also shown you here in this diagram. So now let's move on to this problem. Design a simply supported slab to cover a room with internal dimensions of 4 meter by 5 meter, which is having a thickness of 230 mm, and 230 mm thick brick walls all around. Okay, so the slab, it is supported 4 by 5 slab. It is supported by a 230 mm thick wall on all of its four sides. Okay, so this is a wall like this, and it is having a thickness of 230. Use M20 concrete and Fe415. Assume slab corners are free to lift. What does this mean? Free to lift.
Unrestrained
This is
slabs.
unrestrained slabs. So purposely I have put this question because restrained slab questions are very lengthy, and I think if you are able to understand the procedures of unrestrained slabs, you will be able to do restrained slab also. Only the thing you have to carefully look at those 9 conditions which I have also made you understood in this class. So let's proceed with this problem. So first of all, the first step is I will have to find the effective depth. So in the previous class, I have shown you different values of L by D L by D ratios. So for simply supported, it was 25. So those are not present in IS code. Sorry, I didn't tell you this. Those values are recommended values, which you can get it from some books. This recommended value, if you adopt it, there are low chances like your beam will fail in the deflection test which we do it at the end if you follow these recommended values. So for simply supported, the recommended value is 25, and since this is a two-way slab 4 by 5, if you do 5 by 4, sorry, if you do the ratio 5 by 4, it will be less than 1. So this is a two-way slab, and two-way slabs, they are more safer than the one way slab because they are deflecting in both directions. So now I am applying a factor of 1.15 because the depth we can reduce if it deflect in both the direction, if we are allowing the deflection in both direction. This is based upon only the, I won't say this is based upon experience, but based upon the numerical calculations. This is recalculated, and we found that the depth, it can further reduce by a factor of 1.15 because two-way slabs are more safer than one-way slab. But you can also directly take this value 25 and proceed, but that would give you a higher value of D, and that would be uneconomical. But these all are things for future, more for more expert designs, but for the time being you can take 25 value also. But now I am considering 1.15, reducing the depth by 1.15, and to find the overall depth, what I am doing, I am adding it up with effective cover. So effective cover, how I can add the effective cover. Nominal cover, I am taking it as 20 because they have given it here. Nominal cover is 20, and if I am adding it with the effective cover, so what will be effective cover? Half of the diameter of bar, CE will be Cn plus half of the diameter of bar, so that will be 25. So 140 plus 25 will give me 165. Sorry, 140 plus 25, yeah, that's correct. Now next will be to find the effective depth in both the directions, because now I have a two-way slab, so both of the depth is important. So you all must be knowing that the most predominant or the most uh, so this is the deflection diagram, and the most critical deflection is in the x direction, and the next critical direction is the y direction, because the shorter span, it is more stiffer, and the stiffer the side, the more critical it will be. That's why x direction, it is more critical, hence we provide bars in the x direction. We provide the bars in the x direction in the lower part, and above these bars we will provide the bars in the upper direction. So if you have a slab, so if I draw the cross section like this, and this is Ly, this is Lx. So I will provide the bars in the shorter direction at the bottom. like this it should be. I'm sorry. In the shorter direction, I will provide the bars first and then along the long direction, because the shorter direction it is more critical. Okay, so dx I have calculated it d minus c. C is the effective power 140, directly this one, and dy, that is further I will have to minus one bar minus half of this bar. So if I'm assuming the bars to be of same diameter, I will have to subtract this by 10, so 130 mm. Now I will calculate the effective depth. Effective depth is nothing, effective span, sorry. The effective span will be Lx plus d, that is clear span plus the effective depth. So for Lx it will be Lx plus dx, and for Ly it will be Ly plus dy. And the Ly by Lx ratio I am getting it as 1.239, which is less than 2, and I am concluding this to be a two-way slab. Now let's calculate the load on the slab. So I already know the total D is 165, and based upon the unit weight of concrete I have calculated the dead weight of the slab. And after adding this dead load with what, with the finishing load, I'm getting this as the total dead load. I already know the live load, and the total load can be calculated as 1.5 times dead load plus 1.5 times live load, and then the bending moment can be calculated. How it would be calculated? Based upon Ly by Lx ratio. I hope you are familiar with these ratios, the formulas from where it came. And if you are not familiar, you can directly also get this ratio from IS 456. Now I will calculate mx and my. Mux is alpha x. Please remember, for both mux and muy, here we have lx square, not, many people make mistakes taking ly square for muy, and they correctly calculate mux, but for muy they mistakenly take ly here. Don't do that. Now for both the direction, what will I do? I will calculate the percentage of steel. Before calculating the percentage of steel, I will calculate the r value. R is mux by bd square. This many times we have seen how this we are doing it. Now I will calculate the percentage of steel. So I get 0.275 percentage in x direction and 0.204 in y direction. So if I multiply this percentage of steel by the area, effective area, then I will get the area of tensile steel required. Now I am assuming, I have already assumed this 10 phi in the previously before starting the problem. Now the spacing would be calculated based upon this 10 phi diameter, and those spacing would be limited into 1 meter strip. So this spacing has to be cross-checked with maximum spacing, and it should be always less than this maximum spacing. If it is more, just go for the maximum spacing criteria. So provide 10 bar to 200 center to center, and 10 bars in the y direction, 290 center to center. So these are the bars which are provided based upon the bars which were required. Now based upon this provision, I am calculating the area of steel provided. So this is the area of steel provided. Now we all can give the deflection check L by D. So that deflection check I have not included here in this slides, but the reinforcement detail I am doing it here. So here you can see this is a discontinuous slab. So for discontinuous slab, since both the edges are discontinuous, I am providing the curtailment only up to 0.1 Lx and 0.1 Ly on both the sides. Okay, so this was all about today's lecture. So we have seen the curtailment of continuous slab, curtailment of two-way slabs, and the torsional reinforcement requirement, and one problem on two-way slabs. If you all have any doubt, you can ask me.
Sir, if the slabs are supported on beams and columns, then some special precautions are to be taken or not?
How you can say a slab is supported on beams or columns? Okay, so you are
Beams and
okay. I
columns.
I I
Frame.
understand what you are saying. Here we are calculating it for simply supported.
For the walls, the supports are walls, na here.
Yes, yes.
So if it is beams and column, then
So
uh,
we have already seen it, right? If it is supported on beams or columns, it will be a case of continuous slab, now. So at continuous, you know the moment coefficients, how to calculate it.
yes, sir. But we have frames here, if we get frames here for the different slab panels in that case.
If in case of frames, in frames the slabs, how would it be different? Only the thing is the load on the column, it will be more at different points,
Okay, sir.
while the slab,
So
yeah.
so for means any kind of special means we can use the same formulas here, है ना?
Yes,
Uh,
yes, yes.
okay,
Only the thing you should know is the dead load and the lab load on this slab.
okay,
On,
sir.
only the design of columns will change.
And sir, the bending moment and shear force coefficient in the one-way slab, sir, if there are beams, in that case, if we if we just provide, sir, the walls in case of beams, then can the coefficients be used?
In case of beams, if in case of walls, if you provide beams.
Means I'm saying that in the case we are when we are using the coefficients, the bending moment and shear force coefficient in one-way slab. In that case, we had the beams in between.
Okay.
Do you remember that? Uh,
Yeah, if you are talking about beams like this, these are
uh,
secondary beams, right?
Second, where have you are you showing something
Yeah,
on the
yeah.
board?
Here, here. This is secondary beam.
Oh, okay.
This is
Yes.
primary beam.
Uh, the secondary beams, yes, sir. Where we find the coefficients. Uh, in that case, if it is replaced by walls, then can we use those coefficients there as well?
Yes, yes. You can use the beams. Like, don't get confusion between beams. Whatever we provide it, the beams are just to support the slab, like the way we are supporting it on the wall. Okay.
Okay, sir.
Only the beams will do it. It will make our slab more restrained because it will be a monolithic construction. And if it is resting directly on the slab, then we will have to provide the torsional reinforcement in order to stop the upliftment of this slab. Okay.
Okay, sir.
Any other question from anyone?
In the chat box, sir, somebody has.
Okay. Sir, for compression member, what is effective length in respect to the major and minor axis? For compressive member, you are talking about columns. What is effective length in respect to the major and minor axis? Okay, I'm not able to understand your question properly. Effective length, okay, so are you talking about different support conditions? Effective length for different support conditions are you talking about?
Hello.
Yes,
Hello.
Mithilish.
Yes, sir. Sir, in clause 25.1.2, they are given that short and slender compression